Okay, that's me. Welcome to a second session in week 3, I believe. That's the week 3. That means yesterday you did have a session about techniques of integration, which this means that we did start chapter 7, and you did learn integration by parts, section 7.1. And the second section for this week is this one, trigonometric integrals, 7.2. That means I will introduce this topic. I will show you a few other techniques for the trigonometric functions, which of course trigonometric functions are everywhere. Even integration by parts that you learned yesterday, you also have always somewhere trigonometric functions. And before I start, just one more thing. Please always, because I'm getting an emails like how can you practice, what the best source of problems. That's mean one more time, I'm reminding you that I did add extra module. I think I call practice with Kasia, and I'm like solving for you lots of different types of problems, but they are extremely helpful for your weekly quizzes and of course midterms and final. Okay, that means they are like specifically the exam type questions. That means please always, sometimes when the session is longer, I mean the practice session, you can just pick the problem that you like to master and you can just like go through the problems that you like. But I will recommend that you practice and you confident with all of the questions in that video. Okay, and of course, the weekly live sessions are also extremely helpful, and especially when you're really attending, okay? Okay, that's me. Let's see what we have. Trigonometric integrals. That's me. Let's see. I can tell you that yesterday that integration by parts was totally new technique, right? It was like the big, nice formula, which the opposite, which is the differentiation technique, is behind, which was the product rule. Right? That means the product rule for differentiation corresponds to integration by parts. But this one is probably, I would say, is just a little bit of trigonometric. Have to recognize them and use the U substitution. That means this section is not extremely a new technique. It's just a little bit different angle looking at two concepts at the same time. And that's me. Let's see what we have to know. I will. Why I can't change my slides? Okay. That means, as I mentioned, we have to know a few identities. The first one, of course, is the known one, is Pythagorean identity. Sine square of x plus cosine square of x is 1. And what we will need sometimes, you can see what I did, we have to know how to rewrite sine function in terms of cosine, or the cosine function in terms of sine. And that's me. And especially the square. We know that trigonometric functions, trigonometric ratio are based on the right triangle. Everything is based on the Pythagorean identity. That's we like a squared, b squared, c squared. That means especially when we have even powers, it's so easy to rewrite one function in terms of the other. Because if we will have just sine of x, I can still rewrite sine of x. I can put maybe square root plus or minus, but then I think I'm kind of complicating. Okay, that means let's say we will focus on the even exponents. And then we can also look at the higher exponents like sine to the power of 4. I can rewrite as a sine squared and again squared. And sine squared, of course, is 1 minus cosine squared of x. Okay? Or even higher, 10. 2 times 5. That's square, that's 5. Oh, and we can, of course, we can keep working, keep going with them. Please remember that the even exponents are quite good to rewrite using the Pythagorean identity. Okay, what else I have? Double angle formulas. Okay, we also remember from pre-calculus, sine of 2x is defined as a 2 sine of x cosine of x. Of course, I'm not going to prove this. You have to believe me that that's true. Probably some of the pre-calculus textbooks, they include the proof. Okay? We can prove numerically, if you wish, like we have to remember that sine of 2x, I will switch off video because I'm covering part of the screen and I need the entire screen. Okay, that means I can just show you, like, let's say sine of 2 times 30. Of course, we know that this is 60 degrees. Do you know what is sine of 60 degrees? What's the value? Somebody remembers? Unit circle? Yes, sine, this is, if you like, pi over 3. Square root of 3 over 2, okay? But sometimes we think, I don't want to say this because that's not true, that we can say, we can take sine of 30 and multiply by 2. Of course, that's not right? Because sine of 30 is 1/2 times 2 is 1. That means that's the reason that sine of 2x is not just 2 times sine of x. Please remember, I can remove that, but I can definitely use my formula, 2 times sine 30 cosine 30. And let's check. 2 times sine 30 is 1/2. Cosine 30 is square root of 3 over 2. I can cancel out and I do have the same answer. Okay, that means definitely the formula works. Okay, and then I kind of like divide by 2, but depends what we will need. Of course, I want you to know this one. Sine of 2x. Okay, another one is cosine of 2x. Cosine of 2x looks a little bit maybe more complicated because it's defined as a cosine square of x minus sine square of x. And what we can do, I didn't type this, we can try, because we can see the squares, we can try to rewrite this formula in terms of cosine only or in terms of sine only. That means let's try. Cosine square of x is defined as a 1 minus sine square of x. If I will subtract another sine square of x, this is equivalent to 1 minus 2 sine square of x. That means just in case, if we will need cosine of 2x in terms of sine function only. Or I can say sine square of x is 1 minus cosine square of x. Then what I have? I do have cosine square of x minus 1, and negative will give me 2, give me positive, and then I will have 2 cosine square of x minus 1. That means double angle formula for cosine of 2x could have this form or this one, okay? But if you remember the boxed one, cosine square of x minus sine square of x, then you can rewrite, because Pythagorean identity, everybody knows. Okay, double angle. Now, let's actually take, that's what I just got. Let's take the cosine of 2x in terms of sine and cosine of 2x in terms of cosine. Okay, and what I will do, I will solve these equations, 2 equations. One of them, the first one, I will solve for sine square of x, and the second one, I will solve for cosine square of x. Okay, that we can see. I did subtract 1 from both sides, and I divide by -2. Okay, the same on this side. I add 1 to both sides and divide by 2. That means what we have, this is also an important formula. So, okay, sine square of x could be rewrite like this one, and cosine square of x could be rewrite like that. You may notice that and sine and cosine includes cosine of 2x, cosine of 2x. Yeah? Please do not make the mistake for the sine function. This is still cosine. And since this is 2x, you can see double angle, and the original expression is the half of this angle, x, we call half angle formulas. Okay, that's when we do have double angle and we have half angle, because x is half of 2x, of course. That means if this is x, this is double. If this is x, this is double. Okay, let's practice half angle. We know this. Now, just in case, if you have to rewrite sine square of 2x, okay, using the half angle formula, we can see I have to double because 2x is half of the right-hand side expression, 4x. And the same for this one. And the same, 3x, 6x. If this is 3x, it's half of 6, and so on. 5x, sine square of 5x will give me 10x, and one more, 10, 20. Okay? And please notice again the cosine for both of the formulas. For the sine function, we have minus, negative, negative, negative. For cosine, we do have positive addition. Okay, that's me. Now let's see how we can use these formulas. What I have. Of course, talking about the trigonometric integrals, we have to know the direct, the immediate antiderivatives. Integral of sine of x is negative cosine of x, we remember that. And integral of cosine of x is positive sine. Because if I will take sine of x, derivative of sine is cosine. Derivative of negative cosine, it's positive sine. It's just a fundamental theorem of calculus. Okay, that's me. Let's see what kind of integrals we may ask you from this section. The first one will look like that. That means we will have a combination of sine function and cosine function. That means the only thing that we're gonna focus on an integral, sine of x times cosine of x dx, and sine, it's gonna be taken to the power of a number n, and cosine is gonna be taken to the other number m. Both of them are just the counting numbers, natural numbers. 1, 2, 3, 4, 5, 6, 7, whatever number we want. And now we will have a few cases, okay? That means if this is the first case, if both of the numbers are even, okay, even numbers, like 2, 4, 6, and so on, we have to use the half angle identity. Okay? We have no other way to simplify or to integrate this. Okay? That means if both of them are even, that means let's see. I will pick first one, like this one, and this is quite frequent integral. Make sure that you know how to integrate sine square of x. Because I can assume that I have cosine taken to the power of 0. 0 is not really the even number, but I can. But 0, of course, is giving me 1. Okay, let me just do something. Okay, 1 second, I will just, because my other screen okay, I'm back. Okay, that means what was said, that we have to use the half angle formula. Okay, I mean, I don't have to really go this way. That means, let's see. Did I type? I did type. That means sine square of x, I will rewrite as a 1 minus cosine of 2x over 2. Okay, and we can see how nice it is. Now I don't have any square. I only have 1 minus cosine function. I can have 2x as an inner function. We know how to deal with this. And 1/2 I can put like in front. Okay, having square, I really have like a product, sine of x times sine of x. And we learned yesterday the integration by parts. We may try integration by parts, but probably will not really work, because integration by parts, it's especially for the product of two functions. Okay, that means this one, we will not think about integration by parts. We will use half angle formula. And now what I can do, integral of 1 is simply x. Integral of cosine of 2x is sine of 2x over 2. Okay, and done. Yeah, I don't have to, I did multiply by half, I did distribute half, but we don't even have to. Okay, we can see how fast we can integrate sine square of x. And that means, please remember, half angle formula. And I think I do have, oh, I make the common denominator. I have cosine square of x. It's gonna be identical steps. The only difference is addition. Okay? That means it's 1 plus cosine of 2x over 2. We can put half outside. Integral of 1 is x. Integral of cosine of 2x is sine of 2x over 2, or times half. Distribute half, common denominator. Okay, the same thing. Okay, let's see what next. Okay, next one is, oh, I did increase a power. Okay? That means this one is good for homework assignment, maybe, or for extra practice, but sine square of x and cosine of square of x is no question, okay? We do have to know. Let's see this one. We remember what I did on the second slide? I did something like that, because we do like square, like the even powers. And now, for the sine square of x, I'm gonna place half angle formula. 1 minus cosine of 2x over 2. However, I still have additional square. That means what I will do. 2 squared is 4. That means I will place 1/4 in front of the integral. And now I have to square this. Okay, and we know that if I will FOIL this, I will have 1 squared, then I will have negative 2 times cosine of 2x, because I will have twice, and then I will square the last quantity. Okay? It's like a minus b squared. A squared minus double ab plus b squared. That's what I am using, if you like to use right away this formula. Okay, that's me now what I have. I can definitely integrate 1. I can definitely integrate cosine of 2x. I have again square. Yeah, that's not good. That's product. But what I will do, I will use again a double half angle formula. That means I did copy this. I put down this, and cosine square of 2x is defined as a 1 plus cosine of, I have to double because 2x was half, 4x over 2. Okay, now no squares. Now I can integrate term by term. Oh, okay, let's see. I did copy 1. I did copy this. And this one I just split for 2. Because 1 is affected by 2, that means it's half. And cosine of 4x is also affected by that 2 in the denominator, which is half. Okay, and now integral of 1 is x. Integral of cosine of 2x is sine of 2x divided by 2, but we did have coefficient 2. That means 2 divided by 2 gave me just 1. Okay, and then half is half of x. And now I have 1/2, a constant. Integral of cosine of 4x is sine of 4x divided by 4. Half divided by 4 gave me 1/8. Okay, and then I just simplify. I did add like terms. X plus half x, 3/2 x, copy this function, and that's it. Okay? That we can see the main thing is this one. Exponent 4, 2 and 2. And another half angle formula. Okay. Okay, now we do have a typical, that's what I was saying, typical product of sine and cosine taken to the power of even numbers. That means you can probably guess I'm gonna use half angle formula for sine of x and cosine of x. For sine is minus, for cosine is plus. Okay. What I will recommend, because I did, yes, I will recommend you to solve maybe after this session, or maybe, and I mean in any convenient time, please solve these integrals again. Okay, cover the solution and solve it again. Like write it down, and then you will see. You will really build your your skills, your knowledge, and then you will be extremely confident. Okay, what I have, it's a product. 2 times 2 is 4, no problem. But this one I have like conjugate expression. 1 minus cosine of 2x, 1 plus cosine of 2x. A minus b, a plus b. And we know that this is a squared minus b squared. That means 2 times 2 is 4. And then I have a quantity 1, squared 1, and the second quantity squared, and minus, always minus. Okay. We see a square. I will use the half angle again. Cosine square of 2x is 1 plus cosine of 4x, because 2x was half angle. And let's integrate. I did divide 1 by 2, which is half. 1 minus half is half. And then cosine divided by 2. And now the integrals. 1/2 x and copy 1/2 integral of cosine of 4x, sine of 4x over 4. Done. Did I have? Yes, I have one more. I factor out 1/2. Either way is good. Okay, but the point on this slide is to know that we're using half angle formulas. Okay, let's see. Now we do have a second case. Still sine of x times cosine of x, but now 1 power is odd, 1 power is even. Okay? That's mean now I can give you a little bit of suggestion, but you have to like figure out which way will be good. Okay? And what we will need? We will need this Pythagorean, because what we will do, if we will see 1 power odd, 1 power even, we will probably leave the even one. We have to focus on the odd one, okay? And the odd number we will rewrite as an even plus the remaining one. Okay? Like let's say if this will be 5, then I will rewrite that sine to the power of 4 times sine to the power of 1, for example. Okay, but let's see. And then I will pick one of this substitution. Let's maybe do an example, and then I can show you. But you will know which one to choose. Because I don't want. Oh, okay. Can you see my second slide? I'm changing slide again. Look at this. It's almost the same instruction. It's this. I mean, it is the same instruction if both are odd. That means, let me change one more time. I'm coming back to the previous slide. That's the previous slide. Okay, one is odd, one is even, the exponent. And we will try to do the u substitution, maybe sine, maybe cosine, depends which one is odd, which one is even. Or we do have exactly the same instruction if both of them are odd. Right? That means this is kind of like a third case. That means now let's take a few integrals. First one, cosine square of x, sine square of x times cosine of x. Okay, that means cosine is definitely, that's the really nice odd number 1. Okay, that means what I will do, this one, we can almost see right away if I will let u, because I have to use the u substitution, if I will let u to be sine of x, I have this formula for my du. Can you see? U is sine of x. Then du is, of course, the derivative, cosine of x dx. That means this is ready to be cancelled out. And the rest of the integrand, it's in terms of sign. That means I only have u squared du. Yes, we can see how nice this is. We can like rewrite right away. That means sine square of x times cosine of x. I would even say that this is like integral from calculus 1. It's so easy to see the u substitution. Okay, integral of u squared is u cubed over 3. And now we have to get back to the x variable. Instead of u, I'm substituting back sine of x, sine cube of x over 3. Okay, let's take more complicated. Okay, 2 and 3. Sine square of x times cosine cube of x. Did I type the solution? Okay, I did type the solution. I wanted to write for you, but I did type. That means that's what I said. What we will do, we will attack the odd number, and I will rewrite as a 2 plus 1, which means I will have cosine square of x times cosine x. Yes, we see this. This is still cosine cube, but now what I'm doing, hold that single one. That means this single one, I can remove that one. It will stay, because this is telling me that I have cosine of x. Cosine of x is the derivative of sine of x. That means what I want. I want the rest of the integrand, the blue part, to be rewrite in terms of sine only. Because if I will let u to be sine of x, I can rewrite everything in terms of u, and this will be du. That means the only thing that I'm not happy, I am still happy, it's cosine square of x is equal to 1 minus sine square of x. We remember that, second slide. Right? And I'm still keeping this. That means now I think we're ready. This is gonna be du, and u, of course, is sine of x. Outside this box, everything is in terms of sine. That means let's do it. Let u to be sine of x. Du is cosine of x dx. That we can see I will have u squared, 1 minus u squared, and this is my du. Perfect. Okay, we can see how nice. Remember to keep that extra cosine, the single function. Cosine or sine, this could be done opposite, like to the opposite functions. Okay, let's distribute u squared times 1, u squared times u squared, u to the power of 4. U to the power of 3 over 3, u to the power of 5 over 5, plus the constancy. And now instead of u, sine of x, done. Okay? But we can see this is maybe the new process. Okay? That means this one is more advanced than the previous one. Okay, let's do one more like that, and then we have another one. Oh, okay, just cosine cube. That means don't worry that we don't have additional function. It's still an odd, and I will follow my rules. I need even, the maximum even. If this will be like, I don't know, 9, then I will put 8 plus 1. Always take the even and plus 1, the remaining one. That means we can see this, okay? I will keep this one. Actually, I'm not asking you a question, I feel bad. Can you tell me what will be the next step? Who can tell me what I have to do with the rest of the integrand? Since I have cosine here, what I need? What function, what trigonometric function shall I see here? Who can tell me? I hope you are still there. I see your names. Can you tell me what we have to do? Yes, thank you, Jessie. We have to rewrite in terms of the opposite function, which is the sine. Excellent, thank you. Thank you for typing, because that's always, and I'm keeping this. And now you see nicely, I'm ready. U is gonna be sine, and the box is du. This is du. 1 minus u squared du. Everything in terms of u. And of course, sine, u, we let u to be sine of x. And now we can see no problem. Integral of 1 du is u, integral of u squared, u cubed over 3, plus the constant of integration, and substituting back sine of x. Okay, that means that the first 2-3 lines are important. The rest of them is easy. Okay, let's see another one. Oh, okay, that means I don't have, I think at the end, few multiple choice. Okay, that means I am assuming that we gonna be okay with sine times cosine. Now what we have another pair of trigonometric functions, tangent of x and secant of x, because they almost are derivatives to each other. Yes, we know we do have a little bit, yes, extra, not just tangent of x sine. Oh, they make some, not just tangent of x secant square of x, I mean secant, we do have some extra things, but we can also make some combination of du and u, some substitution. That's mean now we will use this one. I don't know, oh, why I'm making some lines. I can't remove this one. Okay, let me write one thing. Sine square of x plus cosine square of x equals to 1. But now we need tangent and secant. That means what I will do, because everybody knows this, I think I said this today, I will try to change this for tangent. That means I am gonna divide everything by cosine square of x. Cosine square of x, cosine square of x. Sine square of x over cosine square of x, of course, tangent square of x. Cosine square over cosine square, 1. 1 over cosine, secant square, of course. That can you see? This is Pythagorean identity also, but with, in terms of tangent and secant. Okay? And now I can solve, I mean, I can say secant square of x could be rewrite in terms of tangent, and of course tangent, because we will need also the other way. Tangent is just secant square of x minus 1. And I can tell you also for the next section, I think next week we have 7.3 trigonometric substitution. These formulas are extremely important. Okay? However, I would say every single slide in this session, it's quite helpful and important. Okay, but I know that you're gonna practice, I know. Okay, that's me now, let's come back. This is what I was just trying to show you, okay, how we can derive this formula. That means if you will forget like 1 plus tangent or maybe 1 minus tangent square or maybe the other way, always think about the basic sine square plus cosine square is 1, divide by cosine and get your formula. Then you're not gonna make the mistake. Okay, just a helpful tool. Now let's come back to our function. Integrand, integral. Tangent of x times secant of x, and both of them are taken to the power of nm, the same thing. Nm are the counting numbers, I should, natural numbers. And what we may have. For this one, we will try to make two cases. If both of the exponents are even, then most likely you will do this substitution. You will let u to be tangent of x, and then we will figure out the du and everything, okay? If they are even, tangent. If both of the exponents are odd, we will let u to be secant, because we can see derivative is like odd exponents. And that's me both of the cases. But I can tell you, because don't think like okay, like we may have even or odd. You may also have one odd, one even, okay? And then you will try, because we want you to think like a little bit, not only like follow my instruction. I always want you to understand the concept and then like be creative or like manipulate with these numbers. That's me, just in case if you will see one odd, one even, please try both of the methods. One of them will work. But if you have odd, secant, if both of them are even, you will be tangent of x. And let's see. Oh, I don't know why I have this blue line. Okay, tangent square of x times secant square of x. That's been what substitution we will do? Both even. Who can tell me? Do you remember? I can come back. Even. If it's even, we will let tangent of x, we will let u to be tangent of x. Yes, u tangent. Thank you, Jessica. Thank you. I like the participation. And we can even see if I'm thinking that I will let u to be tangent, I know what's the derivative of tangent. secant square of x. That means I have to save this for the cancellation, for my du. That means that's correct. U is tangent of x and du is secant square of x. No problem, because boxing my derivative, the rest of the integrand, it is in terms of the opposite function, tangent, in this case. Okay, u cube over 3, tangent cube of x over 3. Done. I have this line, please ignore that, I can't remove it. Okay, let's look at the more complicated. Oh, tangent to the power of 6, x, and secant to the power of 4. That means now let's see the process. The process is almost the same like for the sine and cosine, except we have to have even. But first of all, what do you think? What u substitution we aiming to apply? Both of them are even. Oh, Jessica, you can type again. Or somebody else, yes, thank you. Thank you. Jessie, actually, in this case, yes. Okay, that means we aiming to have, yes, we aiming to have the u substitution, I mean to let u to be tangent of x. That means now let's see, if I'm thinking to let u to be tangent of x, I know what's the derivative of tangent of x. Can you actually type for me what's the derivative of tangent of x? What's the derivative of secant square of x? Thank you. That means what I have to do, I have to attack that secant, and I need 2 plus 2. Can you see 2 plus 2? Because I know that this is gonna be my du. 2 plus 2, I have to split it because I need that one secant square to be cancelled out. And now, everything outside this box, the rest of the integrand, since I want u to be tangent, the blue part must be rewrite in terms of tangent. I'm okay with this one, but what about secant square of x? I have to rewrite in terms of tangent using that Pythagorean identity. Okay, do you remember? Who can tell me what is secant square of x in terms of tangent? Do you remember? It's tangent square plus 1. Really good. Okay, I will. Thank you. Really good. You see, that means that's what we have to do. I still have my, I really save this one, and the rest of the formula is in terms of tangent. I think now I am good to do my substitution. U is tangent of x, everything will be in terms of u, and du is ready to be cancelled out with this expression. Okay, I will change this. Okay, u to the power of 6, u to the power of 2 plus 1, and du. Excellent, everything in terms of u. Let's distribute. U to the power of 6 times u to the power of 2 is 8, 6. Integration, 9, 9, 7. And substituting back in terms of u, tangent of x. Okay? That's when we can see this. I want you to be confident, especially with the first, okay? The first step. If it's even, attack the secant. Okay? Okay, let's see what else I have. Oh, odd. Okay, tangent to the power of 5 of x times secant to the power of 3 of x, both odd. That's me now, my first question. What substitution are we planning to apply? We will let u to be, is odd, secant of x. Thank you. Oh my gosh, you're learning really fast, guys. Good, good. Okay, that's me now, secant of x, correct. Now my next question. What is the derivative of secant of x? What is the derivative of secant of x? Can somebody type for us? It's secant tangent. Thank you, Jessie. Secant tangent. That means now we have to think and we have to like visualize. Okay, I really want in that red box at the end, I want secant and tangent. That's what I'm gonna do. I'm gonna steal one tangent from here, and I'm gonna steal one secant from here. Can you see? I did I have to, yes? I don't know what you think, but I have to have my secant tangent. We know why. We know why. That means you can see I did steal one tangent, I did steal one secant. It's only 4 and 2. Okay, that means since this is derivative of secant, I need the entire integrand, the blue part, in terms of secant. Okay, that means I'm okay with this one. Oh, tangent to the power of 4. I have to rewrite this in terms of secant. That means the first thing, oh, I should maybe, I thought that I typed. The first thing I will rewrite maybe on the side, tangent square of x and another square. You remember that exponent trick, okay? Because we know what is tangent square of x in terms of secant, and then I have to square it. That means that's what I did. This is tangent square, I mean everything. Oh, I don't want to remove my, I have my secant square. Tangent square is, this is tangent square, right? Tangent square of x and another square. And let me box my du. Okay? As we can see, secant square I did copy, tangent square is inside, and an additional square because was there. Okay, now I'm ready. Oh, really? Why I type this? Let me put one more time. I was really expecting my U substitution here. Tangent, square, and square. I'm just trying to make sure that you know the exponent for. Okay. What we have? We do have now secant square, which is u squared minus 1 additional square, u squared, and of course du, because du is just the derivative of secant, which is ready. We kept that derivative to be cancelled out, to be rewrite as a du. Okay, that means this is, of course, because of that extra square, looks complicated, but we still managed to rewrite in terms of u. I will distribute this. First of all, u squared minus 1 squared is u to the power of 4 twice u squared times negative 1 and plus 1 squared, which is 1. And still u squared, and I did distribute u squared. Okay, I don't want to show you this too fast. That's the next line. And maybe one more time, if we have a minus b squared, one quantity minus the second quantity squared is a squared, 2 times ab plus b squared. Okay, yeah, just please remember it's not just a squared minus b squared, but we know that. Okay, no problem. U to the power of 7 over 7, u to the power of 5 over 5, keep the constant, cube, and substituting secant. Okay. Looks like lots of work, but it's not. For me, the important part is second line and the third line. I mean the second step and the third step. Yeah, that's important to know what's going on. Okay, let's see what else I have. Oh, please ignore that line. I do have exam type question or the quiz type question because it's multiple choice. Okay, that's me. You will tell me, did I type the solution? Okay, I didn't type the solution. Great. I will write with you. Okay, what do you think? What we aiming? What substitution? Tangent of x or secant of x? Odd, which means, thank you, which means, yes, secant. Okay, that means if I am aiming, shall I write somewhere? I am aiming this, secant of x. Who can tell me what's the derivative of secant of x? Again, you will practice, you will remember forever. Secant tangent, thank you. Secant x tangent x dx, excellent. That means what I need. I need secant x tangent x dx at the end. That means what I will do, I will definitely steal that whole tangent, and I will steal one of that secant. What's left? Secant square, secant, and I can place tangent at the end. It's still there, right? Actually, I can use. That means I need this to be du. And oh, what about the blue part? Can I just keep in terms of secant, or do I have to do something? Is the secant form good for the u substitution? Yes, yes, keep it. Thank you, thank you. Thank you for confirming that we can see this is just my u squared and this is du. Wow, I didn't even expect that it's so easy. You see how easy question we can ask you? Okay, who can tell me what's the integral of u squared? Or you can probably tell me the final answer. U cube over 3, thank you. U cube over 3. And what is the final answer? Which option? A, B, C, D, or E? A. Excellent, because we did play with secant. It's 1/3 secant cube of x plus the constant of integration. A, thank you. You see how nice? Nice, yeah, nice, easy week. Okay, let's see. I think I have another one. Oh, the definite integral. We do have limits of integration. Let's see. Maybe you will see the same integral. Oh, secant to the power of 4 times tangent cube. Do you remember? I said that we don't want to trick you, but we really want you to think a little bit. That means, what do you think? We can always make the mistake and we can come back. Or also, just like from my experience, I think sometimes both of the methods will work. Okay, that means, what do you think? What will be easier? Because I definitely have to steal, if we will let u to be tangent, then what we need? Maybe we can, what's the derivative of tangent? Maybe we can try this. If we will let u to be tangent theta, who can tell me derivative? Yes, we can. I think we can follow the even method. Even if this is odd. Derivative, thank you, Jessica. It's secant square theta d theta, or x dx. I mean, we do have. That means, let's try. What I need, okay, I will keep this one. Secant square, that's what I was trying to. That means I will say 2 and 2 because I have to steal one secant. Secant square theta, and I will put tangent cube theta, and at the end, I will keep this. Okay, please correct me if I'm wrong. Okay, that means this is my du. And the rest of them, I need in terms of tangent. Okay, that means this will stay. And who can tell me, how can I rewrite secant square of theta in terms of tangent? Yes, thank you. Let me finish this. Secant square theta d theta. You see the settings, and Jessica is telling me tangent square plus 1. Excellent. Tangent square theta plus 1. Okay, now I think I'm ready to rewrite everything in terms of u, because my blue part is in terms of tangent, which will be easy to write in terms of u. And this is my du. I can use blue color. Okay, that's me what I have. I have u squared plus 1, u cube, and this is du. Really nice. U to the power of 5, u to the power of 3. If we will do this distribution, we adding the exponents, right? We remember. Okay. Integrate u to the power of 6 over 6, u to the power of 4 over 4. The only thing is, for the definite integral, I don't have to rewrite in terms of tangent theta. I can find a new limits of integration. That means let's find a new limits of integration. New limits. If theta was 0, u is defined as a tangent of 0. Who can tell me what's tangent at 0? 0, thank you. That means not changing, 0, 0, 0. Now, if theta was pi over 4, you see u will be tangent at pi over 4. Who can tell me this? It's 1, thank you. Oh, we love the limits from 0 to 1. That means that's the new limits. Let me box nicely for you. 0 and 1. And then I can substitute 1 will be 1 over 6, 1 over 4. Substituting 0, of course, is 0. Oh, who can tell me the final answer? Fractions. 1 over 6 plus 1 over 4. I think 12. It's a good denominator. 5 over, yes, I think good. That's, oh, do we have, yes, we do have that option. 5 over 12. Okay, that means this is, yeah, it's, I mean, it's nice integral. Maybe it's a little bit longer because of the new limit, because of the arithmetic at the end, a little bit of unit circle, and of course, the main thing that I was teaching you today. Okay? That means what we can do, let's finish, because I'm still worried that I lost my writing, hopefully not. Let's finish the session, and you can definitely, I will solve a few more problems for you, and check the folder, the module practice with Kasia, okay? I will put extra practice for 7.1, integration by parts, and extra practice for this trigonometric, okay? I hope you did enjoy this session, okay? And I hope you learned something that you can check that week. Okay, good luck with your weekly assignments, and you will hear from me next week. Thank you.